Thank you very much. And I want to thank the organizers for giving me this opportunity to speak at this wonderful workshop. I'm sorry that I cannot be there in person. Okay, so the first thing that I want to do is tell you about a special class of hyperuniform materials that we call Stealthy Hyperuniform. If you're interested in learning more about hyperuniformity, and especially if you're an insomniac, I highly recommend reading this review article at night because it's guaranteed to put you to sleep. Okay, now, so this is not clicking properly. Yeah, does anybody know how I could get rid of this at the top? Because I don't normally see that at the top. Yes. Yes. Thank you very much. I appreciate it. That worked beautifully. Okay. For some reason, it's not clicking. I don't know. Okay, here we go. So let me just tell you very quickly the outline of the talk. First, I'm going to give a very, very brief review of hyperuniformity. Then I'll tell you about the special class, Stealthy Hyperuniformity, and order across length scales. And then I'll get into the novel optical properties. All right, so first, let's say qualitatively, what is hyperuniformity? A hyperuniform many-particle system is one in which large-scale density fluctuations are greatly suppressed compared to those of typical disordered systems like liquids. Turns out that all perfect crystals and perfect quasi-crystals are hyperuniform. So hyperuniformity provides a unified means of categorizing and characterizing crystals, quasi-crystals, and special disordered systems. So you can think of hyperuniformity then as generalizing the traditional notions of long-range order that we learned from perfect crystals, crystallography, and quasi-crystals. But now it includes disordered systems, exotic ones. And you can think of these disordered hyperuniform many-particle systems as new ideal states of matter in that they first behave more like crystals or quasi-crystals in the way they suppress large-scale density fluctuations, and yet are also like liquids and glasses since they are statistically isotropic structures with no Bragg peaks. They can exist as both equilibrium and non-equilibrium phases. They come in quantum mechanical and classical varieties, and they're endowed with unique bulk physical properties. Okay, now a little more quantitatively, and this is the first paper in which we introduced it. This was with Frank Stillinger in this rather simple fundamental study of density fluctuations locally. This was back 2 decades ago now. It seems like many, many years ago. And so the idea is you have an infinite set of points in Euclidean space, and this is what I mean by d-dimensional Euclidean space. And of course, that can represent anything you like, stars in a galaxy, trees in a forest. In fact, we recently applied the hyperuniformity concept to galaxy distributions, for example. Anyway, so you have an infinite set of points in Euclidean space, and I'm depicting things in 2 dimensions for visualization. And on the left, what I'm doing is I have this window, this observation window of radius r. I'm going to imagine that this is going to be a very large window. I'm going to move it from place to place. As I move it from place to place, the number of particles that I find within the window will fluctuate. So I have a random variable, which means now I can define the variance, the standard variance, local number variance associated with that radius in the standard way, okay? And typically what you have is if you have a typical disordered system, it turns out that, and including Poisson point patterns and many correlated disordered systems, right? So I would say these are garden variety disorder. The variance grows like the radius to the dimension, the volume of the window. And we're going to call any pattern whose variance grows more slowly than r to the dimension hyperuniform. Now, this implies that the structure factor, which you can get from scattering, single scattering, in the infinite wavelength limit goes to 0 as k goes to 0, as it turns out. Now, if you have a crystal, it's very, very clear that the variance should grow like the surface area of the window, since the fluctuations are concentrated near the interface, not in the bulk. And so it's not really surprising in the case of a crystal that the variance grows like the surface area of the window, but it is much more of a surprise. And of course, at this time, in 2003, we knew of very, very few systems, and we hypothesized the existence of some of these disordered varieties that behave just like the crystal on very, very large length scales. Now, that was really kind of unheard of at the time. And we did various studies and proposed various kinds of systems that might have this behavior. But we knew very, very little at that time. So again, hyperuniformity provides a unified means of categorizing and characterizing crystals, quasicrystals, and special disordered systems. I don't have time to tell you how you can rank order quasicrystals and how you can rank order crystals that are hyperuniform and compare them to disordered hyperuniform systems, but you can go to that review article, and if you're awake at night, you'll be able to look at it. Okay. Now, just to give you an example, since that time, since 2003, we have learned of many more systems that are now disordered in hyperuniform. Disordered classical ground states, maximally random jam packings, fermionic point processes, charged hard sphere systems, self-assembled bidisperse emulsions. By the way, this is by various groups, random organization models, vortex pinning in states and superconductors, so-called perfect glasses. You can find them in natural systems like avian photoreceptor patterns. For color sensing, I mean, this is a really interesting optical application, but this is natural. And it turns out that it's very, very useful to drive systems that are not exactly hyperuniform, disordered and hyperuniform, to being more hyperuniform. And when you do that, you end up getting improvement in the physical properties, like say, the electronic band gap in the case of amorphous silicon. Okay, so that's a whirlwind tour through the original setting within point configurations. Now I want to talk about the context that I'm going to be speaking about today, and that is two-phase media, composite media. And that system, you could also talk about hyperuniformity. And in this case, you don't have density fluctuations, point number fluctuations, you have volume fraction fluctuations. And so you can then, the way you defined it in this particular case, and I don't have time to describe this, the volume fraction variance actually scales for typical disordered systems like 1 over the volume. This is just a different definition, just a different scaling that leads to 1 over the volume for typical. If you have a hyperuniform disordered composite, it actually goes faster than 1 over the volume. And that's equivalent to the following condition on the spectral density, which again is going to be the Fourier transform essentially. Well, it is exactly the Fourier transform of the autocovariance function. And that means that this goes to 0 as k goes to 0. Now, I'm showing you 2 illustrations in 2 dimensions. If I scale the volume fraction variance by r squared, if it's non-hyperuniform, it'll tend to a constant value as r increases. So it saturates, asymptotes to some constant value. Whereas if it is definitely disordered and hyperuniform, it will be a descending function and will actually, continue going down. Here we have the corresponding spectral density for a non-hyperuniform system. And you can see that as k goes to 0, spectral density is not going to 0. And then this is the corresponding hyperuniform one, where it is indeed going to 0. Now, you can define, if anybody is interested, and I don't have time to talk about this, you can define local order metrics for two-phase composites. In other words, order or disorder on local length scales using this particular metric. Okay. Now, I've told you that in the previous slide, I told you that you can have faster than 1 over the volume growth. Now I'm going to tell you that you can have 3 different types of scaling laws. So let's imagine that the spectral density scales like k to the alpha as k goes to 0. Alpha is greater than 0, then you have 1 over r to the d plus 1. That's class 1. That's the strongest class. Then if you have alpha is exactly equal to 1, you have a logarithmic correction. And if it's class 3, which is the weakest, alpha is between 0 and 1. Now, it turns out class 1 includes all crystals, many quasicrystals, and exotic, disordered media. Now, there is a special class that I want to focus on because that's going to be what I'm going to be describing in a little while, and that is the stealthy hyperuniform class. That's also class 1, but this is really the strongest form of disordered hyperuniformity that you can have, where you have 0, not just as k goes to 0, but in a region around the origin up to some capital K, some cutoff. Okay. Again, this is really, really bizarre behavior. I can't impress upon you how bizarre this is. I wish I had more time to tell you about the structural features of this. I will say a few words about it, but I'm not going to be able to do justice to it. Okay, now, the other thing that one should understand about this is that even though hyperuniformity talks about infinite wavelength density, infinite wavelength behavior, and a particular type of behavior in which k goes to 0, which the structure factor goes to 0, or the spectral density goes to 0, it brings to attention the validity of looking at the large scale properties, even if the system is not hyperuniform. So general non-hyperuniform scalings. Well, you can think of alpha 0 here as being typical non-hyperuniform disordered behavior. And then if you have alpha between a minus d and 0, that's anti-hyperuniform, because in this particular case, the spectral density is in fact diverging as k goes to 0. Okay. And so those are anti-hyperuniform examples. And in that particular case, you're talking about systems at critical points, including fractal structures. So fractal structures would be considered to be exactly anti-hyperuniform. Therefore, you can think of this then as being a way of classifying all translationally invariant states of matter according to their large-scale fluctuations. All right, now I would like to just show you, give you a feel for spectral densities if you haven't really looked at them, but I know that a lot of you have, but maybe some of you have not, and I'm going to show you 3 different hyperuniform models and 3 different non-hyperuniform models. In the case of a crystal structure, so you have a simple cubic packing of spheres, you're going to have Bragg-like peaks, okay, that are descending. Okay, that's expected. This is a disordered packing. It's that we call maximally random jam packing. Basically, you take marbles, you put them into a container, you shake them up, roughly speaking, and you densify the system, and this is what it looks like. Those systems, maximally random jam packings, are in fact hyperuniform. And here is an example of a stealthy packing, okay, where you have 0 up to some cutoff, and then it goes to its asymptotic values, which is actually well defined. These are the systems that I'll be focusing on in a little while. 3 different non-hyperuniform models. So this is what I call Debye random medium, definitely not hyperuniform. Overlapping spheres, okay? And then an equilibrium packing of hard spheres. So this is an equilibrium packing along the disordered branch. And again, it's not hyperuniform. All right. Now, I want to just say a few words about the fact that you can generalize hyperuniformity to many other situations. Random scalar fields. You can show, for example, that spinodal decomposition is an example of a disordered hyperuniform state. You can think about random vector fields, tensor fields, for example, vector fields that you would get in turbulence. You could also imagine statistically anisotropic materials in which now, instead of having a circular region around the origin in Fourier space, you can have this figure 8 where there's absolutely no single scattering events. And you could actually produce these kinds of anisotropic structures. But here, the point is that you can have so-called directional hyperuniformity. In this direction, it's not hyperuniform. And if you go approach it in this direction, the origin, it is hyperuniform. So those are interesting. And I think those are waiting to be applied more fully to optical applications. Okay. Now I want to talk about how you can generate these really bizarre, disordered, stealthy hyperuniform states. In fact, they're actually ground states, which is really also bizarre because when you think of ground states, you don't think of disordered states typically, especially classically. That's what they are. Now, how do you produce them? So these are in these early papers with Frank Stillinger and students. You imagine that you have n particles with some configuration under periodic boundary conditions in a box, in a fundamental cell, with a pair potential, V, that is bounded with a Fourier transform. So V tilde is the Fourier transform of the pair potential. You can write down, because of the setting, you can write down the total potential energy as the standard way, sum of pairwise terms. Or because of the way I set up the problem with periodic boundary conditions, you have the Fourier representation of this, which is a sum over wave vectors. And inside here, you have the Fourier transform of the potential times, in this case, the structure factor, okay, that I mentioned earlier, plus a constant that is independent of the structure, okay? Now, here's the trick. You have V tilde, and you say, okay, I'm not going to specify the direct space potential. I'm going to specify the Fourier transform. And I'm going to say that it is positive up to some cutoff and then 0 otherwise. So it has compact support up to this cutoff. All right. And here's an example of a step function. Now, if you put particles in a box and then you have an optimization technique, let's say you put them in randomly, and now you're going to move the particles around in such a way that you force the structure factor to be 0, where this has support, then you can see that if you can do that, you have conflicting step functions, and therefore you actually have arrived at the ground state. So the corresponding real space, direct space potential is this oscillating quantity, which is reminiscent actually of Friedel oscillations in the quantum mechanical problem. But anyway, they're soft bounded interactions. And so when you can do this, these are always going to be class 1. They're always going to be stealthy. We call them stealthy because there's no single scattering for all these wave vectors. And when they're disordered, they're highly degenerate. In the infinite system limit, they actually become infinitely degenerate. And so you can think of these as classical analogs of quantum spin liquids. Okay. Now, somebody might ask, well, to what extent can you actually show that they are actually ground states and that you've achieved ground states? I'll answer that question in a few minutes. Stealthy patterns can actually be tuned by varying the size of the exclusion region, the region in which you're constraining the structure factor to be 0 for those wave vectors. And so that you can think there's a tuning parameter that's associated with that. It's going to be the ratio of the number of constrained degrees of freedom that I just mentioned to the total number of degrees of freedom in the system, which is essentially the dimension times the number of particles. Okay. So as you tune chi, right, as you make chi bigger, you're constraining more and more wave vectors around the origin to be 0. Now, these stealthy systems have this very hybrid crystal liquid nature, because here's a diffraction pattern for a crystal structure, and I'm showing, and by the way, the definition of hyperuniformity always excludes forward scattering. So if you look at the origin here, you see, obviously, in the case of a crystal, there's a circular region around it, which is black, which means that there's no scattering at all. Now, if I had shown you this disordered pattern up to that cutoff, you would have thought it was a crystal, right? Because I'm only showing you up to here. But in fact, beyond this cutoff, it's diffuse, okay? So this is what I mean by this hybrid crystal liquid nature. And there is a theory that goes with this, which is really highly non-trivial, because the dimension of the configuration space is actually changing as you change chi. Normally in statistical mechanics, the dimensionality of the configuration space always stays fixed because the number of particles is fixed. Anyway, the point is that you can actually get, when you do these computer simulations, you can get down to 0 very, very, very nicely to something like 10 to the minus 21, right? So we regarded that to be a great success. And by the way, 10 to the minus 21 is at the very least what you need. So if you're going to produce stealthy systems, you want to do at least as well as 10 to the minus 21. And we can show theoretically that if you don't produce really, really high quality stealthy configurations, you're not going to get you're not going to maximize the optimality of the properties. Okay, so anyway, here is a picture of a configuration when chi is relatively small, 0.04. Okay, this is a stealthy system, and here's an example of a system where chi is much larger, 0.41. Now you can see that as chi increases, as it turns out, the entropy of the system decreases, and the short range order increases. So not only are you controlling the large scale density fluctuations, you're actually controlling also what is occurring at intermediate length scales as chi becomes larger and larger. Now, to capture the degree of order, the translational order, we introduced this tau order metric that is defined this way. You take the structure factor, you subtract off the Poisson, which is 1, square it, you integrate this up to some cutoff, whatever you desire. And that's going to be a measure of the translational order up to that particular wavelength. Now, another important thing is if you increase chi above 1/2, the system undergoes a phase transition to ordered phases. So this is going to be the disordered regime, and this is in 2 dimensions and 3 dimensions, the disordered regime, and then eventually you end up getting crystal structures. Now, I don't have time to tell you, but we actually have written a paper that's posted on the archive with a postdoc, Peter Morse, and Paul Steinhardt and company, to create now extremely large stealthy systems, because there was a stumbling block in our previous techniques, which we have overcome. And you can get now down to 10 to the minus 55 with hundreds of thousands of particles. So if you're interested in learning more about that, you can go to the archive. All right. Now, let me bring attention now to the novel properties that were discovered, I would say prior to this paper, but around this time. And so this is a paper with Marian Florescu and Paul Steinhardt that we published in 2009. Now, about a decade and a half ago, it was believed that you needed to have Bragg scattering to achieve cellular solids with complete photonic band gaps. But that turns out, and especially photonic band gaps, they're comparable in size to a photonic crystal. But what we did was we took these stealthy disordered patterns from this collective coordinate procedure that I just described, which is an optimization procedure. And then we mapped them into networks, dielectric networks. We did a particular type of a tessellation called a Delaunay centroidal tessellation, which is not the normal Delaunay, okay? Anyway, so here's a picture of the network. And, whoops, what happened here? Okay, so we then carried out carried out calculations on the computer and looked at the band gap formation. And you can see this is the band structure. Chi is equal to 0.1, 0.2, 0.3. You start to see the development of the band gap. At 0.4, it's very, very clear. And then at 0.5, it's the largest that it will be, but it's definitely there. And in addition, with that tau order metric, you can see how the tau order metric, as you increase chi, increases, okay? Which means that this is really what you need to be able to achieve these fairly substantial band gap sizes, okay? Then with our experimental colleagues, we took these computational designs and we actually made materials that work in the microwave regime to test out the idea, the computational design. And you can see from the top what it looks like. And the beauty of the fact that you have these very large isotropic band gaps is that you can create crazy waveguides with these kinds of crazy geometries, which turn out to be much better, superior than photonic crystals because you have less loss. Okay, now since that time, there have been many, many studies, and here's this is a very partial list, and I apologize to those in the audience who may have done work on this, but it's going to be extremely difficult because there's so many people that have worked on this. So I would say the one that was one of the interesting ones that followed up on this was work by the French group here, where they were looking at transparency in 2D stealthy disordered point scatterers, as it turns out. And then TM polarization, the Sheffield group looked at the stealthy hyperuniform patterns, and they came up with a phase diagram as a function of chi, which showed transparency, diffusive PBG, and localization regimes. And then another group showed that stealthy hyperuniform composite lenses can dramatically reduce backscattering relative to its periodic counterparts. We obtained predictive theories for effective dynamic, elastic, and dielectric constant across the first 3 space dimensions. I'm going to say a few more words about this in a little while. In another 3D study with Luca Del Negro and company, we showed that these systems have weak localization transparency regimes that depending upon chi. And then Vicente and company have actually done a lot of work on this. This is just one of their papers where they show robust phononic band gap formation in 1D. And then I like this particular paper, this more recent paper, where people have shown that you can get 65% sunlight absorption in a 1 micron silicon slab with this kind of a texture. Just to mention other properties besides optical, you can show that if you look at steady state heat conduction or electrical conduction through a network that is hyperuniform, stealthy and hyperuniform, you can get almost optimal performance. And the same thing is true if you decorate the points by spheres and look at these as obstacles and then diffusion transport outside, you can show that these are nearly optimal effective diffusion coefficients. Okay, so why do these disordered patterns, stealthy patterns with sufficiently high chi values, yield desirable physical properties? Well, first of all, they're rotationally invariant disordered materials. that, as I said, that are kind of hybrid states between liquids and crystals that maximally suppress density fluctuations from intermediate to infinite wavelengths. And they have this bounded hole property that I have not said anything about so far. You cannot have arbitrarily large holes. They're prohibited, right? So usually a disordered system, as you approach the infinite system limit, you can have arbitrarily large holes. You don't want that property, obviously, if you're a theoretician and you're worried about the thermodynamic limit. So I'm not going to have that much. I want to make sure that I cover other material. So this brings up the natural question. There's a conjecture that I had described in this review article. High chi, stealthy hyperuniformity is a necessary condition for an isotropic disordered network to have a complete photonic band gap in the thermodynamic limit. Okay? Now, so this was done with Michael Klatt and Paul Steinhardt recently. We used a two-scale ensemble approach to be able to do this, okay? And except for the high chi stealthy, and we looked at a variety of different disordered states, including hyperuniform ones that were not stealthy. And we showed that the winner that emerged among all of these possibilities was only the high chi stealthy. So let me just show you, because I do want to talk about other things. These network models we called equiluminous, random sequential addition, stealthy non-hyperuniform, perfect glass, low chi stealthy hyperuniform, high chi stealthy hyperuniform. The red code is to mean that it doesn't satisfy the conjecture. The green means it satisfies the conjecture. And these are the only two that satisfy possibly the conjecture. Well, of course, this one doesn't because this says it's low chi. And it turns out that the one that emerges, but we're interested, I should emphasize, in what would survive if you were able to go to the infinite system limit. And this is the only one that survives, which does not mean it actually it does produce a band gap in the infinite system limit. We can't prove that, but it definitely tells you that it has a higher place among all of the possible structures. Now, in another study with Joe Kim, who's a postdoc, and was a former student, we looked at a theory, which I'm going to skip at least on this slide, where we looked at both the dynamic elastic problem as well as the electromagnetic problem. And we showed that there was a commonality between them that enabled us to eliminate this common feature between them in the exact expansion that involved the spectral density. Because of that, we were able to then come up with cross property relations. So if you have phononic information, you can predict electromagnetic information and vice versa. Then the last few slides that I want to talk about have to do with delving more deeply into the electromagnetic problem that I just was alluding to. And in this particular case, I have the same setup as before. You have a two-phase system. You're sending an electromagnetic wave. And I want to ascribe an effective homogeneous dielectric constant to it. Normally, when people have done this, you can only apply it in the quasi-static regime, the long wavelength regime. What we wanted to do was we wanted to extend this to include wave numbers that are well beyond this quasi-static regime. And so we call this non-local formulation. And the reason why it's a non-local formulation is that the average polarization depends on the average so-called cavity field at other positions through this kind of a operator. So I don't have time to really tell you about the gory details of this, but that's the basic idea. So it's a non-local theory in that sense. Okay, so anyway, when you turn the crank, you end up getting this expansion, okay, this expansion, which is an exact expansion, And the thing that I want to bring your attention to is that this is actually a fractional linear transformation of the effective dielectric constant tensor. And on the right-hand side, the parameter that is involved in the expansion is this generalized polarizability that I call beta PQ, where P and Q are either phase 1 or phase 2. P is equal to 1 or 2, and Q is equal to 1 or 2. Okay. And then these coefficients are second-order tensors that are functionals that involve the set of correlation functions S1 to Sn. What are these? These are Sn is the probability of throwing n points into the system and the n points falling into one of the phases. And they're going to be products involving the principal part of the dyadic Green's function. Now, the formulation applies to very, very general systems, but a very important quantity here is the perturbation parameter. And it turns out the thing that you have to realize is that this actually depends on the exclusion region associated with the singularity of the dyadic Green's function. So depending upon the choice of that shape of the exclusion region, you can get different expansions. And it turns out different structures demand different shapes to choose in order to get fast convergence of the series. That's the basic idea. So if you choose a spherical exclusion shape, there's one choice. If you have a disk exclusion shape, there's another choice of structures. Okay. Now, if you truncate at the lowest level up to the 2-point level, and then 3-point is and higher is 0, then you can write down things in terms of this functional f of k, which is given in terms of the spectral density, and we call this the attenuation function. So this is a key quantity. But the thing that I want to bring your attention to is that this is really a multiple scattering. This is actually going to account for multiple scattering, primarily because this is a fractional linear transformation. And it has very, very fast convergence properties. We've tested this out for various systems. And so you can view this as these non-local formulas are really resummed, and I mean the truncated forms, are resummed representations of the expansions that still accurately capture multiple scattering. And it predicts, this theory predicts, when you truncate it at the second term, it predicts a fully transparent regime for these wave vectors, incident wave vectors. And you can see that it involves capital K, the cutoff. Okay, so the first thing that we did here was we tested it using FDTD calculations for simple cubic structures to show how the prediction compares to the simulations. And we also compared it to Maxwell-Garnett quasi-crystalline approximation. And in all cases, for the real and the imaginary part, the truncated formula does very well compared to the simulations. So that gave us confidence that for the disordered systems, that we would have accurate results. And of course, we also compared these disordered non-hyperuniform and hyperuniform media to the case of simulations, and again, found very, very good agreement. Okay, so the point is if you believe these formulas, then you have a way of getting estimates well beyond the quasi-static regime for a wide class of composite structures without having to perform full-blown computer simulations. Now, in this very last slide, I want to just tell you about some very recent work that was actually posted to the archive just the other day. This was submitted to Optica, where we took the general formula from the PRX and we applied it to one-dimensional layered media. We were keenly interested in the stealthy hyperuniform variety, but of course the formulation applies to any structure. But a particular interest in this very short paper was the stealthy hyperuniform variety. And again, you can see what I just mentioned earlier, that you predict a perfect transparency interval up to this finite wave number, where in principle you would have no Anderson localization in the infinite volume limit. Of course, this is not a proof because you have higher order terms, but we know for various good reasons that even if there is Anderson localization in the infinite system limit, for any reasonable finite size sample, the localization length would be much, much bigger than the sample size. And you can then compute with this theory. You can do it for various chi values. And it turns out in the case of 1D stealthy hyperuniform system, the disordered regime is actually less than a third of chi. Chi has to be less than a third. And we showed with this that you can actually compute the transparency expression exactly, which I don't have here. But you can then determine what the dependence is on the contrast ratio, because that is gonna make a difference. So you can look at it for various chi values, and of course it's descending as the contrast ratio becomes large. By contrast, we can show that the non-stealthy hyperuniform media are not going to be perfectly transparent in the infinite volume limit. That means that there is going to be some degree of attenuation. Now, of course, there are practical aspects to this that I'm not going to have time to describe. So I want to now go to my conclusions. Hyperuniformity provides a unified means of categorizing and characterizing crystals, quasicrystals, and specially correlated disordered systems. Hyperuniformity stresses the importance of long wavelength correlations even in non-hyperuniform systems, forcing us to really rethink what we mean by randomness. And one of the important lessons is whenever you talk about disorder, you have to tell me on what length scale you're referring to. Normally, we don't kind of sloppy about that. Disordered hyperuniform materials are ideal states of amorphous matter that are often endowed with novel optical and other bulk properties that we are only beginning to discover. And that's something that I want to emphasize. We're really in the infancy. And the other point I want to make is that disordered stealthy hyperuniform materials have a very special status for the reasons that I just mentioned, especially in terms of interesting optical properties. We can now produce disordered hyperuniform materials with design spectra. I haven't really spent that much time on that telling you about it, but that's true. Hyperuniform scalar and vector fields, as well as directional hyperuniform materials, represent exciting new extensions. And hyperuniformity seems to have become a powerful concept that connects a variety of seemingly unrelated systems that arise in physics, chemistry, material science, mathematics. I haven't mentioned that actually the prime numbers in a certain Goldilocks interval are actually hyperuniform. Fascinating, as well as biology. And then I want to thank my wonderful recent collaborators on this topic. And I want to thank you for your attention. Yes, this is Ping. Hi. Uh-huh. Yeah, absolutely. That's a great question. That's a fantastic question because we studied amorphous silicon. And what we did was we tried to use the standard kinds of interactions that generate amorphous silicon structures when compared to experiments, right? Now, we could get systems that were going towards hyperuniformity, but never getting there. So we would say that those systems are disordered and not hyperuniform. But I think it raises some very, very interesting questions. I think in the case of the electronic problem, it is much easier to be able to get band gap formation. In the case of the photonic problem, because you have two polarizations, it's much more difficult, much more challenging, I would say. The other point I want to make about amorphous silicon is that because we were able to show that if you drove the system to being more hyperuniform, even if you didn't get there, the electronic band gap increased. And that caused some experimentalists to go back to Argon, where they had done experiments, X-ray experiments, to revisit samples that they had, and found that there were some systems experimentally that were very, very close to the ones that we had predicted, at least computationally. And so I think it's a very, very interesting question, and I think there's many, many different aspects to answering that question. Sure. Yes. Yes. It's a fantastic question. Okay, so one of the things that I would say first is that when we think about two-phase composites, right? And we're not talking about point scatterers anymore, right? When we talk about two-phase composites, we're scattering off the entire volume, right? And so what I would imagine that you would have to do in that particular case is see how the frequency response of, say, the scatterers. First of all, I don't know of any theory that does it, so it would be a very interesting thing. Maybe you could tell me, right? But then how would the structure, how would the hyperuniformity then change the answer from when you did not have that kind of a response? And I don't know the answer to that question. Maybe you could shed some light on that. I mean, because I think it's a fascinating question. I mean, I think it's just a question of, I believe that there's no question that the stealthy hyperuniform ones would still do extremely well, okay, compared to anything else. That I think I would say. But I think you have to develop the formulation. Yes, yes, yes. And the thing is, I am not aware of any, interestingly, I'm not aware of any study that has systematically done that. Yes, absolutely. I mean, if you have some ideas about that, I would love to speak to you about it. Thank you very much.